Good morning, everyone. My name is Travis. I'm an undergraduate in physics at Portland State. I'm also minoring in chemistry, and I work as a tutor for physics, chemistry, and math at the Learning Center. Um, we're starting off this new lecture online format so a tutor can go through and explain and work problems and examples for problems in the physics classes that are a little bit more tricky and usually homework problems and going to show up in quizzes and exams and stuff like that. So the basic format here is we're going to do a quick review of concepts and of the basic concepts you cover throughout the week, as well as work through some of those homework problems as well. I do want to, before we start, is it Lev5PDX? Hey, thanks for doing this. You're very welcome. I'm happy to do it. I just wanted to share some links with y'all. So there's a link there to the Learning Center's tutoring website, if I'm throwing my pen around, as well as the Learning Center's Facebook and Instagram. So you can follow them for more information and updates on new resources that they have as well. If you guys have any questions at all, feel free to post it in the chat. You do need a Twitch login to throw through the chat at the moment, but that's quick and easy to do, and then you can interact with me on this level as well. I also have drop-in tutoring for 1 hour after this. That's going to be from 4:30 to 5:30 tonight. Feel free to stop in there and ask for any further clarification. We can go in one-on-one depth or more in depth into any of these problems, or I can answer any other additional questions you have as well. There's a bunch of other tutors as well. You can click on one of the buttons above me. There should be a subscribe or make an appointment, schedule an appointment meeting with other tutors or with myself. Feel free to click on that in the Pinji app as well. So the basic idea, we're going to talk a little bit about electric charges, electric forces, and electric fields in this one. I think I have just a basic overview of electric charge, 2 or 3 problems with electric forces, and then we're going to review electric fields as well. All right, so let's get started. So the electric charge is basically any particle can have a charge associated with it. That charge is usually relative to the charge of an electron. So the charge of an electron, we can write usually as E minus is equal to 1 point, or in this case it's a negative, so we say negative 1.602 times 10 to the negative 19th power. And those are measured in a unit called coulombs. So coulombs is really just the way we measure charge, and all charges in nature are going to be basically quantized based on a certain number of electrons or positrons for that matter, because there's also a positron, which is just a positive electron, has the same charge, 1.602 times 10 to the negative 19 coulombs. This is just a positive thing. So some combination of positive and negative charges are going to represent all the electric charges we know of in the universe. There's also subatomic particles and fundamental particles like quarks, top quarks, bottom quarks, and other things like that that do have partial charges, but you're not going to see those independently. They're always going to be bonded together in a more complex particle like a proton, for example. So any charge that we see, we usually would call charge as a Q, is going to equal some positive or negative value, and it's going to be N, which is just an integer multiplier of the electric charge E. So N can equal some discrete value, 1, 2, 3, etc. of that charge. So you're not going to get 5.76 times the charge of an electron. It's going to be a discrete value, 1, 2, 3, 4. It could be 137, but it's still going to be a whole number basically. And that's the general idea of an electric charge. Now, when different electric charges get in proximity to each other, they can apply a force on each other. And that's the next thing we're going to kind of cover, is the electric force. So the electric force, otherwise known as the Coulomb force, I can't spell half the time, but that's why I'm not an English major. The Coulomb forces, and the equation for those you should see pop up on your screen above me right now. It's going to be 1 over 4 pi epsilon naught times the charge of the one particle and the product of the charge of the two particles divided by the distance between them squared. And what do we mean by that is if you had, say, one particle, and we're going to call this one Q1, And you got another particle kind of off in the distance over here. Let's call this one Q2. There's going to be the distance from the center point to the center point between them. Let's draw a straight line. And I'm going to call that R. And it's always the center of the charged particle to the center of the other charged particle is going to be our distance in R. So we can use that equation to find out the force between them. And a lot of times that value of 1 over 4 pi epsilon naught, okay, that's really going to be equal to a standard constant, because 4 and pi are constants. Epsilon naught is also a constant. It's the permeability of space in a vacuum. So that's going to be equal to, go on to this one. Okay, that's referred to often as K, which is equal to 8.988 times 10 to the 9th power. And the units for that are going to be in meters squared newtons over coulombs. And you notice when we plug these units in there, those meters squared newtons over coulombs, it's going to or it should be coulombs squared. They're going to cancel out the charge of the right side of that equation. So coulombs times coulombs, because those charges are going to be rated in coulombs, will cancel out the bottom, and your distance R in meters is going to cancel out those meters. You're going to be left with a unit of force. Force is newtons, is the idea. And I really like the idea of kind of doing the dimensional analysis and breaking down the units for things. It helps me make sure I'm keeping everything on track correctly when I do things. So when we calculate the force for these, we want to draw like a free body diagram. So I'm going to do that next. If we're going to tell about the force from 1 to 2, so for the choice of charge 1 on charge 2, okay, that's going to be equal, and this blue might be a little hard to read, let's change. So the force of 1 to 2 is equal to, it's going to be K, that K value I wrote up there, times the charge of Q1 times the charge of Q2, all divided by that distance squared, R squared. And we know if these values, to say if it's a positive value on both of them, okay, remember that positive charges are going to repel each other. And they repel each other in a direct line between them. So the direction that they're going to repel is going to be in this direction here. So starting from the center, going out this way, just following that line that intersects the center of both of those two. That's going to be basically our force 1, 2 going on there. If they were different charges, if one was positive and one was negative, then it's going to be an attractive force. So those forces are going to pull those particles together, and that force would then lie more on the inside, going in this way, like this. So that's the general idea of Coulomb forces. Any questions on that before I move on to an example? All right, let's go on to an example. So here, we're going to calculate the net force on charge 2, and that's the middle charge in the middle here, from both charges 1 and charge 3. And then we're going to state the magnitude and the direction of that force. So here we have 3 charged particles all in a straight line. You see this first one is -4 microcoulombs, the middle one is 5 microcoulombs, and the one on the right here is -6 microcoulombs. The distance between them, since they're drawn on this axis, we know is going to be 4 centimeters here, because this is lying at x equals 0, this lies at x equals 4 centimeters, and this is at x equals 10 centimeters. So we can find that distance by taking 10, subtracting 4, and we get 6 centimeters here. So we want to draw then a free body diagram, and we want to, on charge 2 in the middle, and determine the kind of the relative magnitude of those two forces, what we think is going to happen. I always like to make a prediction, like, oh, this is how I think it's going to be, this force is going to be greater than this one, and then let the math kind of prove me right. And if it proves me wrong, then I can go back, double check my math, or double check my understanding of the work. So in this case, we're going to have a free body diagram. So if the force of 1 on 2, so that's the force of charge 1 over here affected on charge 2, since charge 1 is negative and charge 2 is positive, we know it's going to be an attractive force. So that we know that force is going to move towards the negative x-axis in this case. So it's going to go somewhere, let's make that a little thicker, along the lines of that. Now, in the other case, charge 3, that's a -6 microcoulombs. So it's a negative, and charge 1, I overwrote it, but it's +5 microcoulombs. So that's also going to be an attractive force. Now the question is, relative to the force 1 on 2, is that going to be greater than or less than that? And we can determine that based on the product of those two charges and the distance between those charges. And then the distance between those charges, if we look at the equation above me, matters a little bit more, because when we take that distance and square it, that value becomes a lot bigger. So that value should have more of an impact, because when that is larger, we're going to get a larger value. So in this case, I would predict that this force is going to be a little bit smaller than the other one there. Now let's go through the math and see how that works. So the force of 1 to 2, in this case, is going to equal K times the absolute value of -4 microcoulombs times the absolute value of 5 microcoulombs. Yeah, absolute value divided by 0.04 or centimeters squared, or say meters squared. And if I do the math here, drop the absolute values, make everything positive, and square the bottom, I end up with 20 microcoulombs divided by 0.16 meters squared. And we can plug that into a calculator, and we can determine our forces. Times K. Okay. So let's plug that into a calculator real quick, and we can determine what our forces are. So I said K is equal to 8.988 times 10 to the 9th power. And we're going to multiply that times 20 times 10. Let's do the same, E to the -6, because that's going to be microcoulombs. And we're going to take that whole value. Just forget my parenthesis at the beginning. We're going to divide that by 0.16 meters squared. And what did I screw up on? Do I need a parenthesis here? No. Wonderful. Oops. All right, let's try that again. I think I had the E in the exponent, which it didn't like. So it's 8.988 e to the 10, or e to the 9 times 20 e to -6 divided by 0.16. Still with a no. All right, I'm changing it to the times 10 then. Times 10 to the power of 9 times 10 to the power -6. That worked. Huge number. 20 to the power of 6, 10 to the power of 9. That's a much different value than I got before. Something's not right. 1 second. Better calculator. 1/4 pi. epsilon naught times 20 times 10 to the negative 6 microcoulombs divided by 0.16. I guess, yeah, it's the same. Okay. Seems to be a lot of force. Okay, so we have that's 1.1 times 10 to the 6. I'm not liking that. 1.1 times 10 to the 6 newtons. Let's try the force from 3 to 2. 0.0016. Yes, thank you. Thank you, Ricardo Pinji. To the negative 12. 10 to the negative 12. That would probably change everything, wouldn't it? Let me do that here real quick. That's what I get for trying to do math in my head. And here I'll put values in here. And that should be Coulomb squared. Of course, that looks a little bit better. So 112 newtons is what we're getting there. So yeah, that would be, let me fix that. 10 to the negative 12 coulombs squared, and that's going to be 0.0016 meters squared. That's 112. I was just off by a few points of magnitude. 0.35. Is it B HomeQuest 11? Which calculator are you talking about? This calculator? Or this calculator? The fancy one? That's a TI Inspire app for the iPad. It works just like the TI Inspire handheld calculator. It's really useful. It has all the units built into it, and it does all the conversions for you. I love it. I highly recommend it. I'm a calculator nerd, so yeah, the Inspire is a great calculator. Highly recommend it. They have an upgraded version that has a little blue on there. It's the Inspire 2. It's also a great calculator. Just to do calculators for a second, the TI-84 is also a great calculator. The CE version. It's a wonderful thing. Okay, so doing the same thing now for the force from 3 to 2, we can see that we have K, we have the absolute value of negative 6 microcoulombs times the absolute value of, let me move that down, of 5 microcoulombs divided by 0.06 centimeters squared. Do my math right this time, and I can get, again, this is going to be 30 times 10 to the negative 12 coulombs squared divided by 0.0036 meters squared. So that's going to equal then let's try it on this one again. We go 30 times 10 to the power negative 12 divided by 0.0036, and I'm going to move back over to here so I can put in that 9.988, and I erased everything. Insert 9.988 times 10 to the power of 9, and then I want to put at the times 30 times 10 to the 12th. And that looks like it's 83.23 coulombs, if I got everything in there correctly, which seems a lot more likely. 83.23, I said. Let's just slide it like that, and I can see my screen. Okay, so the force from 1 to 2 is pulling on the negative x-axis, so this is going to be a negative value, this 112. The force on 3 to 4 is going to pull on the positive axis, so this is going to be a positive value here. So when we sum up those two forces to find our net force, we're going to do the force net is equal to negative 112.35 newtons plus 83.23 newtons, which is equal to, and I can 112.35 plus this value. Of course I need the negative. Calculators are not always happy. There we are. Negative 29.117 newtons. So that's going to be the magnitude of the force, and the direction is going to be towards the right. So I can say it's this big arrow. Nope, it's going to be a small arrow actually this way. That's going to be the magnitude of the force in the direction. So it's going to have 29.117 newtons towards the x-axis. Any questions on that problem? I know I rambled around a little bit with the calculator, but thanks to some help, I got it all straightened out. Now we're going to move on to the next one. The next one uses 2 dimensions instead. So this is a very similar idea. We're going to calculate the net force on the charge at point 2. Point 2 is going to be the top charge up here. This is 2. And we're going to calculate the net force from charge 1 and charge 3. So in this case here, we have, we can draw our free body diagram on the thing. So we can calculate the distances in R is really what we need to look at first. We know that the distance in R is going to be kind of split here. So you're going to have half of R in this direction, and you're going to have well, let's look at one thing first, just the directions on the free body diagram. So we have a positive charge for Q1, we have a positive charge for Q2. We know there's going to be attractive forces. So we know those charges are going to, those are going to be repelling forces because they're the same charges going to move away from each other. So I know that this force has got to go somewhere up in this direction. Q2 and Q3 are going to opposite charges, so they're going to be attractive forces. So this force is going to travel down this way. And we can say that the y components of these forces here, so this is the force y, and this is the force y, they should essentially be equal and opposite, because we can see that there's some symmetry because they have the same distance here. This is r in the y value, and this is r in the y value. So since those have the same distance, they're going to have the same magnitude, just opposite directions, because this one is attractive and this one is repulsive. I'm sorry, this one is repulsive and this one is attractive. So we can ignore and really just cancel out those y and really just focus on the x component of things. The x component we can calculate then. I'm going to erase this so it doesn't get all cluttered. That's going to be just kind of this guy here. So the force from 1 to 2 is just in the x direction, is going to push out in that direction there. The same force and the same magnitude, and when we add them together, we can do toe to tip, is going to happen with the force of 3 on 2 in the x direction. So we can see that the net force on this, when we add these forces together, force net is going to equal the force in the x 1 to 2 plus the force in from 3 to 2 on the x, which, since those two are really going to be equal to each other because they're the same distance away from each other, the magnitude of that distance is going to be the same here, and the magnitude of that distance is going to be the same there. This is really just going to be twice the force, so from 1 to 2, and we can calculate that fairly easily. We don't have values, so we can just do it general analysis. Q1 Q2 over R squared. It's really R in the x, so it would be this value here. So it would be half R squared. And since we're doubling that, that is going to ultimately end up being our force. And that's going to be in the positive x direction going this way. So we can do the math there. 4 squared is 16, and I think that's going to, yeah, that would flip up to the top. So we'd end up with like 32k q squared over r squared. So whatever values we have for q, since q is the same for all of those charges, and then the value for r we can plug in, and we get our net forces on there. Any questions on that type of problem? The idea of looking at the free body diagram, breaking things up into the components, noticing the symmetry between the y's and canceling those out, and noticing the general symmetry with the same magnitudes in the x direction, so we could just double it without having to calculate each of them individually. All right, we're going to go on then to this guy. So this one's the same idea, but it's a little different. There's not going to be as much symmetry here because we have more of a right triangle versus an equilateral triangle, and we actually have some values in there, so we're going to have to do some calculations. So it's the same idea. We want to find the net force on charge 2 versus charge 1 and charge 3. So 2 is still up in here, and 1 and 3 are down there. So the same idea, I was like starting with a free body diagram. We know that we have a positive charge there and a positive charge here, so we're going to get repulsion with those two. So this force here is going to be going upwards, and that's going to be the force from 1 to 2. We're also looking at the negative charge over in this side. We're going to see that that's going to have an attractive force because here is a positive one. So that is going to follow the line between those two going down this way here. And that's going to be force 3 to 2. Now, we have to break these up into their components as well. So f of 1 to 2 is already kind of in its component. It just goes straight up. It doesn't have an x component, or it's equal to 0 in this case. So that makes that one fairly easy. This other one, f2 or 3 to 2, that one's at an angle. So we're going to have to determine what angle it's at, and just so we can determine the magnitude of that force. So we can figure out this angle here by using the sides that we have. So we have 3 centimeters on this side, 4 centimeters on that side. We can determine what angle that is using the idea that theta, this is going to be theta, is equal to tangent inverse of 3/4. Which, if I plug into my, that's not my calculator, it disappeared. Tangent inverse 3/4 is 36.87 degrees. So using that, we should be able to calculate the direction of forces, because when we break these down, we have, I'm getting a little messy. We have two forces sticking out here. One's coming out this way. That's going to be the force of X in the 3 to 2. One's going to be going down this way, and that's going to be the force from 3 to 2 in the Y. Yeah. And then I'm going to draw this one. Let's draw this triangle over here, just so it's a little simpler. It's getting messy over there. And really, just so it looks the same, put that over there. And this is our magnitude of force going this way. So this is the magnitude F 3 to 2. This is going to be F of X 3, 2. And this is F of Y 3, 2. And we have and this angle here is our theta. Now it makes a bit more sense. So to find out that force, we can use the idea of, we have theta now and we have the magnitude of it. So sine, let's say the force in the Y is going to equal the magnitude times sine of theta. So it'll be force 3 to 2 in the Y sine of theta. And the force in the X is going to equal force in, or this is the magnitude, 3, 2 cosine of theta. All right. So now all we have to do is kind of plug in the values that we have and into our Coulomb force equation to find this magnitude of force. So let's do that. We have the magnitude 3, 2 is equal to K, and it's going to be absolute value of 3 microcoulombs times -4 microcoulombs divided by r squared. That's the distance. The distance there is going to be the one thing I have to find, r. I never did find that. So to do that, we use the Pythagorean theorem. Remember that r squared is equal to 3 centimeters squared in this case, plus 4 centimeters squared. Or we can take the square root of both sides. That's going to be r is equal to be 9 centimeters squared plus 16 centimeters squared, which is equal to 25 centimeters squared. We take the, that's the square root of that, square root of that. It's going to be 5 centimeters. So down here I can make this 5, and I'll make this 0.05 centimeters. And we're going to square it because the value for r is squared for the Coulomb forces. All right, so let's plug that into our fancy calculator and see what we can get. All right, I'm going to do it real quick here. So if I do 1 divided by 4 pi epsilon naught time, and that's the value for k, that's that constant k, times, and we had -4 microcoulombs, so 10 to the -6. I'm going to type in coulomb, let's make that, I'm going to look at positive just because we're taking the magnitude for everything. It'll make things a little bit easier. And the other one was, don't tell me, I could look it up. 4 and 3. Got it. 3 times 10 to the negative 6 coulombs. Divided by, and we had 0.05 centimeter or meters. And that was all squared. And let's get that pi out of there. 43.14 newtons. So this is equal to 43.14 newtons. Now we can substitute this value back up into those to find our sine and cosine. So that's equal to 43.14 newtons. And I'm rounding a little bit. It's best to not round that much, so I'm going to go back and use that same calculator value. This is going to be times sine of theta. And theta we said is 36.87 degrees. So I'm actually going to recalculate that to make sure I get the more accurate number on there. I'll do cosine. The same idea here is for cosine to get that x component. So let's see, tan inverse of, we said 3/4 is equal to itself 0.64. I must be in radians. Yes, I am. Now I'm in degrees. It never likes to give me approximate answers. Okay, so there's that. That's the number of degrees. Go back up to, this is our magnitude of force. We're going to multiply that by the sine of this angle, and we can get the component in the y direction. Which is 25.88 newtons. I'm going to move my force triangle down. So that's equal to 25.88 newtons. Doing the same thing for cosine is easy enough. Paste in this guy, but change it to cosine. So we have the same magnitude, we have the same angle, it's just now we're looking at the adjacent side versus the opposite side. And again, I need to 34.51. So this one's going to be 34.51 newtons. So we're almost done with this. All we have to do now is find this force from 1 to 2, which doesn't require a lot of trigonometry because it's only in that y component. So the F from 1 to 2 in the y is still going to equal K times 3 microcoulombs times 4 microcoulombs. Divide by the distance, which is just going to be 0.03 meters squared. Switching over to our calculator, we're going to do 1/4 pi epsilon naught. So that's our K value again, times, and we had, it was 3 times 10 to the negative 6 coulombs times 4 times 10 to the negative 6 coulombs divided by the distance 0.03 Make sure I got these right. 3 and 4. The distance is 3 centimeters. 0.3 meters squared. It's 119.83 newtons. So that's 119.83 newtons. So now when we sum up these, notice this is an attractive force, so that's going to be a negative value. This is going in the positive x direction, and this one is going in the positive y direction. This is in the negative y direction. So when we add those up, we can say the net force is equal to negative 119.83 newtons plus 25.88 newtons and it would be, yeah, and this is just in the y. We also have the x net, which is just going to be equal to this 34.51. So let's find out the net y forces. Be this, that's a negative value, plus this one. Did I miss my plus? There it is. So it's negative 93.9499. Let's say 95. Negative 93.95. Negative 93.95. And that's going to be in the negative y direction. So since these are in the y, if we want to place them in the vector notation, you add your j hat there, because that's the j direction is the y, and this is going to be the I hat there. And then if you wanted to find the magnitude of those, then it's just using basically the Pythagorean theorem, where you take the square root of the sum of both of those after you square them. So the force net, I'm running out of room, is equal to the square root of 34.51 newtons squared plus negative 93.95 newtons squared. We can do that. Square root of that guy squared plus that was 34 squared. It's going to be equal to that's 100 newtons, 100.088 newtons. I'm running out of room. So this is 100.088 newtons, and that's the magnitude of force, of the net force. To find its direction, we have to again use a bit of trigonometry. I'm going to shrink some of this down so I have some more space. Oh, there it is. Yoink. So since we know our components, the I and J components are these guys there, we can find out, because that's basically saying this force is 34.51 newtons, and then the Y, which is negative, going down this way, is negative 93.95 newtons. So our force is going to be going somewhere between those two to find the angle of it. We have to use I'm going to find the angle between those two. We have to use trigonometry. Yeah, and you would just do x, y. Yeah, so tangent inverse of, and which angle are we looking for? So it's down. Okay, so the opposite is going to be this guy. I always think about my triangle. So if I move that down there, I'm looking for this angle here. So my opposite, which is always at the top, 34.51 newtons divided by negative 93.95 is going to give me the angle here that I'm going to end up with. So let's see what that is. We said 34 is the top. Enter. Paste history. So this is negative 20.17. So that's going to be negative 20 from the positive x-axis. And that would make sense because our vector force wants to go from this area down in that direction. So that's the angle that it would be at, negative 20 point, what did I say? 17 degrees clockwise from the positive x-axis. So this one was our magnitude. This is our direction. With any vector, you need both. And we had them in vector format here. So you could say that the force net is equal to 34.51 newtons. And the I hat plus, or I guess minus, just to write it out in one statement, which I didn't do there. So that gives you your vector components of it there. Any questions on what I've gone through and done there? It's kind of a lot of trigonometry and a lot of piecing things together. But it's really, you find the magnitude of your force, which I did here, right? No. And then you plug that into, no, that was here. The magnitude of the force in that direction, plug it in to find your components, which are these, and you use those to then add up all your components, and then you piece it all back together at the end.